Okay, so reminder, we're still playing with, or we're still within the proof of the genus of a sum of knots is the sum of the genera, of their genera. The plural of genus is genera. And we have seen application, so we saw that it proves that knots of genus 1 are knotted and are prime. So for example, the trefoil is prime. There are no zero divisors, so if the sum of two knots is trivial, then both knots must be trivial. And we will see a few more applications later, but let's first prove the theorem. So, and here is the proof, and the proof is modulo everything about differential geometry and modulo the topology of R2. So modulo the Jordan curves theorem, and modulo like knowing everything about general position and transverse intersections and the like of that. So we started with the easy direction. So the easy direction was, well, the inequality written here. And the inequality written here, there is an obvious way to prove it. So suppose you have two knots, so K1 and K2, and you know, I'm being very schematic because there's really no need for anything else. And suppose each one has its own Ciphered surface. So by the conventions that I've been keeping is that the surfaces are green and the knots are blue. So I'll keep this convention. So you know, each one has its own Ciphered surface. I want to construct a Ciphered surface for the disjoint union, and it's completely obvious how you would do it. Well, you connect the two knots with an arc. You make the arc like the bridge of a connect sum, and you replace the bridge by a band. And you can check that adding a band between two surfaces creates a surface whose genus is the sum. By the way, how do you check that? I mean, you don't need to compute anything, right? You just need to draw it once. And so, you know, here are two surfaces of a given genus. So this surface is of genus 3, and this surface is of genus 2. Suppose I added the whole thing here should have been green by my conventions, I apologize. Suppose I had added a band to connect the two. Well, so if I add a band to connect the two, then now there is only one boundary component, right? This whole thing here is one boundary component, and the genus is, well, there are 3 plus 2 holes, so there's really nothing to show. Okay? Anyway, over here, we had an unexpected difficulty, which is that, well, a priori, we don't know much about the Ciphered surface. So it's possible that, it's possible that the Ciphered surface for the node here would be, I don't know, would somehow completely enclose it. I mean, maybe it would have tunnels and all sorts of things, but maybe it would completely enclose it. How do I know that I can find a path connecting it to the other nodes that would be disjoint? It better be disjoint because, right, the path that I would find, that I need to find going to the other node, better not intersect the Ciphered surface, or else I will get a self-intersecting Ciphered surface after I do this operation. So this path better be disjoint. How do I know that one exists? It's almost silly, but yet it's... any suggestions? Right, the issue is almost silly, but it's not obvious. So, yeah.
So the knot is the boundary of the, sorry.
I don't know who spoke first. I think Chinmaya spoke first, but with the microphone off. So Chinmaya, would you continue?
So the knot is the boundary of the surface. So if you believe that there is an enclosing surface which does not, which separates the space into two path components, then that cannot have a component on the, that cannot have a non-zero boundary, and that means you can remove it from the thing. Is that?
Yeah, that's true. Yeah, you're correct. I could actually make it easier. So, so basically what I want to show is that the knot is exposed. Okay? So, given a knot in a Ciphered surface, I can find a path coming from infinity that connects to the knot and doesn't intersect the Ciphered surface. Okay? Because then I'll do it for both knots and connect them through infinity. Okay? And, well, it's enough to find a path that goes to a point on the Ciphered surface. And then, well, remember that the Ciphered surface is connected. So it means that there is a path in the Ciphered surface that goes to the knot. So just hover over that path. Just hover over that path while staying on a Ciphered surface. So basically, I mean, here is a perhaps a better picture. So here is the knot, and here is the Ciphered surface for it. And suppose I wanted to get from infinity, oops, sorry, wrong color. Suppose I wanted to get from infinity to this knot. It's kind of hidden, right? I mean, I didn't hide it very well, but it's kind of hidden behind the surface. So what I'll do is I'll go from infinity to near the surface. Then, since the surface is smooth and not self-intersecting, I can just walk along the surface. The surface is connected, so I can walk along the surface until I hit the boundary of the surface, and where I hit the boundary of the surface, I can just connect to the knot. Okay? Good. So that's easy enough, but now let's do the harder part. So I want to prove now that the genus of K1 plus K2 is greater than or equal to the genus of K1 plus the genus of K2, and that will complete the proof, because we already have the other inequality. So, well, I have a Ciphered surface for K1 and K2 plus K2, and I need to create Ciphered surfaces for K1 and K2 which cuts the genus, okay, which split the genus between the two. Okay, so again, let me draw it very, very schematically. So here is our knot. So this is K1, and this is K2. I actually don't at all care what K1 and K2 look like, and I've already drawn the connected sum. So this is K1, and this is K2, and the thing drawn here is already the connected sum. What does it mean that it's the connected sum? It means that I can find, or one thing that it means is that I can find a plane that separates the two. So there is some plane that such that K1 lies on one side and K2 lies on the other side, and K1 union K2 intersects that plane in only 2 points. Okay? Now, By the way, I'm saying a plane, and probably if I was more sophisticated, I would say, let's draw both knots, so K1 and K2, instead of putting them in R3, let me put them in the three-dimensional sphere, so add a point at infinity, and then this plane is actually an S2, and actually a two-dimensional sphere, right? Because I'm extending it to infinity. But I'm not sophisticated and it doesn't matter. Okay? So, okay, so now I have my surface. So, I'm not sure how to do, okay, so I have my surface. And let's call it sigma. So sigma is a ciphered surface for K1 plus K2. So the ciphered surface intersects the plane. Maybe I should give a name to, no, let me just call it S2, the plane. Okay? So the ciphered surface intersects the plane. And by differential geometry, I can deform it a little bit so that the intersection is generic, is transversal at every point. Okay? So without loss of generality, sigma intersect S2 is transverse. And then the intersection is just a union of arcs and is a one-dimensional manifold. So it's a union of arcs and of curves, so of arcs and circles. So the intersection is a union of arcs, and there is only one place where you could draw an arc with boundary, because there are only two possible boundary points, and these are the intersection points of the knot itself. So there is an arc connecting the two intersection points of the knot with S2, and again, this is an arc of intersections of sigma with S2. So locally, near the arc, sigma extends, well, in two ways, to the left and to the right. But then there might also be several other intersections which are circles. So there might be this circle, and then there might be another one, and they may be nested inside each other. They may be nested in a complicated way. There may be another circle not nested with them. There may be another circle down here, or another kind. Well, there may be more intersections. Okay? Now, near each of these intersections, the local picture is the same. So near this purple circle, the ciphered surface looks like, well, it extends to both sides, so it looks like a tube, okay, like a green tube coming from one side of the S2 and going to the other side with a purple line of intersection in between. Okay? Now, these circles, all of them have an official outside and an official inside. So let me tell you what it means. So, I mean, the Jordan curve theorem tells you that a circle in S2 divides S2 into two pieces. Okay? And these circles, oh, maybe I forgot to draw one case. There could have even been a circle going all around the line here. Okay? But anyway, so the Jordan curve theorem says that each of these circles divide its S2 into two components. I mean, the circles I drew them like geometric circle, but they could be very, very, very complicated, these intersection circles. Okay? So let's declare, and a priori, these two components are equally valuable. Okay? But only one of the two components will have the line segment in it. So let's call the component that has the line segment the outer component. So every circle has an outer side and an inner side. So this circle has an outer side and an inner side. Okay, each circle has now two sides. And there is an official way to distinguish them. So pick an innermost circle. Since there are only finitely many circles, well, because the intersection is a manifold, compact, whatever, so there are only finitely many circles, so pick an innermost circle C in the intersection of sigma with S2, and let me draw the picture near this innermost. So this is, by the way, a repeating technique. In low-dimensional topology, you very, very often you end up looking at innermost circles and do something to them and do surgery around them, remove them, get rid of them somehow. Okay? So let me tell you what to do with this innermost circle. So, but let me first draw the picture. So you know what, I hope this picture is in your memory because I think I have to scroll it off the screen. So here is the S2, okay? And here is an innermost circle, meaning the outside is here. Meaning, being innermost means that there is nothing in it. There are no further intersections inside its inner side. Now, near this circle, sigma looks like a tube that passes through here. So this is sigma. Okay? So what I'll do is I'll move it to the left, sorry, and then what I'll do is I will replace this. So now I have a tube crossing the S2. So what I'll do is I'll take this disk here, the inside of the circle. By the Jordan curve theorem, it's a disk. So I'll take this disk and I'll make two copies of it and move one of them to the left of the S2 and the other one to the right of the S2. So now the new picture is this. So here is my S2. Sorry, it came out a bit ugly. And I've moved one copy of the disk a bit to the left and another copy of the disk a bit to the right. And let me seal these disks and call the resulting surface sigma prime. Okay? Sigma prime has one intersection less, one circle of it, one component less for its intersection with S2. So sigma prime intersects S2 once less. Okay? Now, what can I say about the genus of sigma prime? So there are actually two cases. Okay? So case one, here are the two cases. So case one, sigma prime is no longer connected. Okay, so so this could happen if, for example, the left side of sigma prime closes into itself. Okay, but then let sigma double prime, so keep only the component. So in this case, keep only the component of sigma prime. So since the knot is connected, only one of the components of sigma prime will connect, will touch the knot. So keep only the component of sigma prime that touches the knot, which is still K1 plus K2, and call it sigma double prime. And then for the purpose of genus calculations, I can do the genus calculation by a simple picture like before. So basically I have a ciphered surface with boundary, and I chose a circle on it and cut it on the circle and dropped one of the two halves. The result is has a lesser genus. So the result, the genus of sigma double prime is less than or equal to than the genus of sigma. And of course I started a proof wrong. So let me go back to the beginning and fix the proof. So I wanted to say, so pick a sigma. I don't want any sigma. I want a sigma whose genus is the right thing. So pick a sigma which minimizes the genus. So this sigma is a genus minimizing, right? It's the sigma which computes the genus. In other words, it's a sigma for which the genus of sigma is equal to the genus of K1 plus K2. But if it's genus minimizing, and I've just replaced it by another surface whose genus is one less, the genuses must be equal, the genera must be equal. So again, as sigma was genus minimizing, it follows that the genus of sigma double prime is equal to the genus of sigma, and it still has one intersection cycle less. So that was one case. And the second case is case 2, this is if sigma prime is still connected. So this happens if the two sides of sigma prime are actually connected via another tunnel, or via the knot itself. Okay? So in this case, you can check. Well, in this case is even more direct. So in this case, the picture is so we have a surface whose boundary is a circle, and we cut it open around some path. So we cut here but seal the wounds. So the result looks like, gee, I hope I'll be able to draw it. So if this was sigma, then after the cut, the result looks like this. So I'm not sure if I'm drawing it right. So basically, I've turned the handle here into two tubes that are sealed. But this is just a surface with a genus 1 less. But that's impossible. So in this case, the genus of sigma prime is strictly less than the genus of sigma, which is impossible because sigma was a genus minimizing thing. Okay? So in any case, we find that we can reduce the number of connected. So basically, it means that the only case was the case 1, and we could reduce the number of intersections. So repeat. So you got a new surface with a smaller number of intersections, and repeat the same process. So iterate until there are no circles in sigma intersect S2. And so the picture looks like, so here is the S2, and here is K1, it passes through. Here is K2. The surface has one side and another side, and in fact there is one line of edge of intersection. So now, okay, so this is the picture for K1 plus K2. But I can very easily generate out of it two surfaces, one for K1 and one for K2. So again, so sigma is this whole thing. Sigma is this whole surface. But what I can do is I can move the line of intersection a bit to the left and also a bit to the right, and while doing it, cut the surface at exactly here, so that I get now a new surface, sigma 1, which is a surface for K1, and a new surface, sigma 2, which is a surface for K2. And you can check that their genuses are, well, all you've done is you've cut, well, you've cut well, you can check that their genuses have, that the sum of the genuses is what you wanted. So you got that, you found, so we found sigma 1 and sigma 2 with the boundary of sigma 1 equals to k1, the boundary of, you know what, let's just make it, the boundary of sigma I is equal to ki, and with the genus of sigma 1 plus the genus of sigma, sigma 2 equals to the genus of sigma, which was equal to the genus of k1 plus k2, but you see, the genus of any two individual surfaces is less than the genus of the actual knot. The knot is is more. The actual knot is the minimum of overall sigma. So this is greater than or equal to the genus of k1 plus the genus of k2, and I hope this is the inequality we were after. Okay? So, next time, I don't know, questions, comments?
Yeah, a question. So, in the connected sum, so that's how I understand the connected sum. We connect via bands, right?
Yeah.
So, I don't understand why we are looking at circles. If we connect via bands, so but if we use the
no, because the problem is, the point is that where was it, the original picture, right? So the problem is that we were given a surface for the connected sum. We had no control over it. It was a surface that minimized the genus for the connected sum, but we have no control over it. Somebody gave it to us. It might, it wasn't constructed as a connected sum of surfaces, right? The knots are we took the connected sum of the two knots, but then we took a surface for the connected sum, and we have no control over it. It could go any way it wants between the two sides. So again, the definition of the genus of k1 plus k2, the genus of k1 plus k2 is the genus of the minimal genus of a surface whose boundary is k1 plus k2. Who tells you that the minimal genus surface whose boundary is k1 plus k2 is simple? Maybe it's very, very complicated. Maybe it's a surface that goes from left to right 18 times. Okay? Something bothers you still.
Yeah, it has to do with the cases. So the case one where you said that sigma prime could be disconnected. I didn't quite get that part.
But that's a different story, okay? So I had this surface sigma which went back and forth 18 times. Okay, or in other words, had a very complicated intersection with S2. I do this surgery to it. So I look at an innermost cycle, and so that nothing intersects, so that nothing goes through this disk, and then I cut the tube and replace it by two disks. Okay, but by 2, so in fact, come to think of it, I have the perfect tool to demonstrate it right here. So here is the surface. I cut it open and I seal this with green material and I seal that with green material. That's what I've done here, right? I mean, from being connected, I went to being not connected. Okay? Now, if I've cut the tube, the resulting sigma prime could either be connected or not. I don't know, that's a sort of, there's no, I mean, right, I've cut something, either I've cut it enough, so, okay, again, if I cut this one open, it's still connected because it's connected through some other tube. But then if I'll cut it again, it will stop being connected. So there are two cases, and I had to inspect the two cases separately. Okay? By the way, maybe I should have, you know, if I'm looking at the proof, the genus calculations were fishy because I've done them by an example. Okay? They actually aren't fishy because this operation of connecting, of cutting, it's very easy to compute what it does to the Euler characteristic. So basically it, I would have to draw it, but it removes one, well, it removes one, what does it do to the Euler characteristic?
It removes an annulus and adds 2 disks.
It removes an annulus and adds 2 disks, but you can turn it, you can figure out what it does to V minus E plus F. And I was too lazy to figure out, so basically the effect on the genus is determined. And once I know, and then, I mean, it's computable. And I just took a shortcut for computing it by doing it on an example. Okay, so the effect on the genus will be the same no matter the effect on the Euler characteristic will be the same no matter how you no matter what the surface looks like. So I just did it on one example. Okay. Anyway, let me move on. So I want to state the next theorem, and the next theorem is actually pretty hard, so I'll prove it next time, but I want to explain it and go through some corollary. So theorem, suppose P plus Q is equal to K1 plus K2. So I write a connect sum of two nodes as P plus Q, where P is prime. I mean a prime knot. So, you know, you expect from arithmetic, right, if you if you find a prime factor of a product, then that prime factor either divides the first or divides the second. And I want to assert the same. So in this case, either P divides K1, or more precisely, P, so either there exists some L, either there exists some knot L such that P plus L is equal to K1. So if P plus L is equal to L1, then you can write P plus Q is equal to P plus L plus K2, and then cancel the P, so, and then NQ is equal to L plus K2, right? So if I write, instead of K1, if I write in my mind P plus L, then now I cancel the P's and I'm left with Q is equal to L plus K2. I don't know that I can cancel P. Okay, we have not yet shown that we can cancel two knots from the two sides of inequality. Okay? But I'm asserting that this is nevertheless true. Okay, the story about cancellation was just to remember what I should be writing. I pretended that I could cancel. I can't cancel, but nevertheless the theorem asserts that this is true. Okay? Or, so the alternative is that there exists an L such that P plus L, so P divides K2, and in which case Q is equal to L plus K1. Okay? So this turns out to be a rather, well, I mean, it will take us an hour to prove this, but I want to show you two corollaries. So corollary one, cancellation actually works. Okay? So if P plus Q1 is equal to P plus Q2, then Q1 is equal to Q2. Okay, again, a priori it's not obvious. So proof, so by theorem, so let's use the theorem where, right, the theorem said if P plus Q is equal to K1 plus K2, so let's take the right hand side as K1 and K2. So let's call this one K1 and let's call this one K2 and apply the theorem. So by the theorem, let's see, so either P divides P, so either there exists L such that P plus L is equal to P, and in which case, so if so this is the first case. If P plus L is equal to K1, then Q is equal to L plus K2. So in this case, Q2 is equal to, Q1 is equal to L plus Q2. Okay? But P was prime. And I just wrote it as a sum. But this means that L must be trivial. But here, L must be trivial, and so Q1 is the trivial knot plus Q2, so it's equal to Q2, Q1. And that's what I wanted to show. And there is a second possibility. So, or P divides Q2, so or there exists some L such that P plus L is equal to Q2, and in this case, Q1 is equal to L plus P, right? But again, in this case, it's automatic. I mean, I just wrote Q1 and Q2 as the same thing. In this case, Q1 is equal to Q2, so we're done. Okay? And then the last theorem, so corollary 2, uniqueness of the composite. So we've already shown that every node can be decomposed into primes. Because, well, you just cut it and then you cut more, and this procedure has to end because every time you cut, you reduce the genus of the parts. But now I want to show that the decomposition into primes is unique. So, corollary 2 says the following. If P1 plus up to Pn is equal to P prime 1 up to Pn prime prime. So if I wrote the same thing where as a sum of primes, where Pi and Pi prime are primes, that came out funny. And also, let's assume that n is less than or equal to n prime. I mean, I could just choose which one is n and which one is n prime. So let's assume that this is the case. Then n is actually equal to n prime, and the pi's are a permutation of the pi primes. Okay, proof. So, oops, sorry. So, sorry. So the proof is by induction on n. So if n is equal to 0, then we have that the left-hand side, right, the left-hand side was the sum of P1 up to Pn, so it's just 0. There are no terms on the left-hand side, is equal to P prime 1 up to P prime n prime. But for genus reasons, the genus here is 0. This is the sum of the genera. All the genera must be equal, and the only way this could, must be 0. And the only way is if all of these are the unknowns. But if they are the unknowns, they're not prime. So it follows that n prime is equal to 0. Oh, and that's it. And there's nothing else to show. Okay, and the two sides are both the trivial sides. Otherwise, so consider P1 plus up to Pn is equal to P1 prime plus up to Pn prime prime. And P1 divides the right-hand side. So P1 must divide one of the things on the right-hand side. Right? Because if P1 divides a sum, we've shown that it divides one of the factors. So it either divides this or it divides the rest. And then it must divide one of the terms here, okay? So P1 divides Pi prime for some I, but then since it's prime, since this one is prime, it must be equal to it. So P1 is equal to one of the Pi primes, but since it's equal, I can use the cancellation lemma and reduce the complexity. So cancel P1 and Pi prime from the two sides, and use induction. And I'm already a minute late, so I'll stop. Sorry for running a bit late. Are you with me? So, I mean, the bottom line is not that we're done, but the bottom line is that this theorem is this one is very, very useful, and we'd better figure it out. We'd better prove it. Okay?
Well, you said that this was not easy to prove, but shouldn't it be more like following the nose on the parameter space and sort of doing a bit of casework? And isn't it supposed to be straight? What goes wrong, basically, when you try to do the straightforward following your nose thing?
I don't know what follow your nose means.
You sort of see the parameter space and you know that since it's a connected sum of P and Q and also of K1 and K2, you can look at the parameter space in both ways and then you intersect the intervals and then you just follow your nose.
So, so let me say the wrong way and then the right way, okay? So this is some complicated knot, okay, which is shown, which is presented as, you know, one mess connected some another mess. But now maybe now I can do a sequence of Reidemeister moves. Okay, so this, or potentially so this mess can merge into this mess, right? And then they can split again in some funny other way. A priori, I have no way to relate this, this splitting into that. So again, maybe I can combine these two and then do a funny isotopy, a funny motion in R3, and then split them apart in a way that's completely unrelated. So that's the wrong way to say it. The more correct way to say it is to say that presenting a knot as a direct sum really means finding an S2 that separates it into two sides. So I have the same knot, but I have two S2s separating it. So I have one S2 and here's another one. The two S2s could be, well, I drew them very, nice and clean, but they could be intersecting in very, very, very strange ways. Essentially, as strange as the intersections that we dealt with before. So it's a similar situation where we have two surfaces intersecting, and they could be intersecting in very complicated way. If we are able to split them, if we're able to somehow move these two S2s apart from each other, then the theorem will be easy. But we were going to have very hard time separating them. Did I answer your question?
So I thought we could just work at the level of the parameter space and say, okay, there are two ways to look at S1 as a union of two intervals inside it. And then you intersect all these square intervals and you sort of work on these patches.
I think I understand what you mean. Sorry,
yeah.
I didn't understand you. So you're saying let's well, a knot, okay, a knot is a complicated mess, right? But its parameter space is just an interval, really, well, an interval with the two ends identified.
Right.
Okay, so you're saying the parameter space is cut.
The circle, you mean a circle, and then I'm decomposing the circle into layers.
Yeah, but let me write it as an interval, okay?
Yeah.
So it's cut as a K1 and K2, but it's also cut by some other way, means as P and Q, and it looks kind of obvious that that P is, okay? The problem is that these are cuts in the parameter space. In the target space, these are not presentations. These do not present the target knot as a direct sum. So the green cut might be somewhere in the middle. Okay? So you have a complicated knot and some cut in the middle, and let's say the end. Let's say this point. So the point 0, 1. So this point is the point where the knot closes. Okay. So you have one interval, and you have another interval, right? Between, there are two ways to go from green to the end point, but the two ways are not knots; they're just intervals in R3. Right? To make them into knots.
Right, you can't find the interval. Yeah, okay, you can't. Okay, I see what.
You don't know.
Right.
You don't know. I mean, if you just have.
Right.
If you just have a knot. So if you just have a knot in R3,
Right.
and 2 points on it,
there's no canonical way to join them and get the
right, there is no
sum.
Yeah, that does not represent the connect sum of the
Right,
knots.
that doesn't mean anything. Right.
Yeah. Okay. So see you on Wednesday, and we're way over time.